Connection diagram for DC generator characteristics or experiments. Any connection will result in different characteristic. So to define the machine characteristic, we conduct some experiments. Here on the screen you see a connection diagram for DC generator experiments. So we want to search DC generator characteristics. Let's examine. Here is the terminal voltage, 110 volts. It is applied to a motor, you see, a motor, DC motor. Here are terminals A and B. It is shunt connected. Here you see excitation coil is connected from the terminal voltage directly. Here is a control rheostat RFM, rotor field control rheostat. It is adjustable, so we can adjust field current of motor, and field current, you know, will generate field of motor. Here's a startup resistor. In Turkish we say yol verme. Startup resistor. Starting or startup. Both are correct. Start up or starting. Rheostat, it is adjustable. We use such a motor just to drive DC generator in the experiment. Here's the device under test, which is generator, DC dynamo. Here are armature labels. I and K, separate excitation coil, driven by an external power supply having 110 volts, separately excited DC generator on the right hand side. Here you see a separate source to drive field current. Here is field current, adjustable by field rheostat of generator. By changing field rheostat here, you can adjust field current, so you can adjust field of the machine. And then here is the voltmeter measuring terminal voltage, and then here's a switch or circuit breaker. Now it is open. Here's a ammeter measuring load current, and here's an electrical load adjustable. Now first of all, let's examine on magnetization curve of separately excited DC generator. I say generator because magnetization curve is valid for motor and generator, but we observe such a curve under generator operation. So we operate machine as a generator to get magnetization curve. That characteristic sometimes called as no load test or open circuit test. In these tests, circuit breaker is off. There is no electrical load yet on the right hand side. So what we are doing, the magnetization curve is obtained experimentally, yes, by rotating the DC machine at a given speed, which is constant, and measuring the open circuit armature terminal voltage, which is EA, as the current in the field winding is changed. Let me explain what I mean. Circuit breaker off means there is no load current, and then come back to figure. There is no current, load current. That means armature current is 0. Armature current again 0 due to open circuit of circuit breaker. And then rotate machine at its a certain value. The DC machine at driven at a given speed, okay, let's say rated nominal speed, and it is kept constant during the experiment. Observe armature terminal voltage. Ta-ta! Here it is, Houston. Terminal voltage. And here's a Kirchhoff's voltage loop. Kirchhoff's voltage law around the yellow loop can be written as induced electromotive force in the armature is equal to resistance of armature times armature current here inside the system, and then it is terminal voltage here plus terminal voltage. In case armature current is 0, induced EMF is equal to terminal voltage. So induced EMF can be directly observed from the terminals. Observe VT with respect to field current. I mean induced EMF with respect to field current as a function of field current. That is called as no load test or magnetization curve. Okay, we keep speed constant. We start from 0 field current and then we increase field current. Terminal voltage will increase. It is equal to EMF when there is no load. And then decrease field current. It comes back in a different path due to hysteresis effect. And then when you continue making these experiments, you get such a loop because there is a residual or remaining flux in the machine resulting remaining EMF. If you have a brand new machine, brand new, it starts from here, saturates and come back somewhere here. That is called as remanence EMF. But after having these tests conducted, you got such a curve or such a curve when you are increasing, when you are decreasing. So that is the average value of the curve. We say average magnetization curve. When you keep speed constant, EMF is equal to Ka times flux times angular speed. That is constant. That is constant. So EMF is equal to gamma, let's say gamma times flux. And you know, flux is a function of field current. That field current generates flux. Flux will generate EMF. In fact, behind the magnetization curve or no load curve, there is magnetic flux. That's it. Such a characteristic will give you information about the magnetization. Flux versus field current relation. Induced EMF will function of speed, you know. We have kept speed constant during the experiment, but if you increase speed, there's a new curve which is twice of the previous one. That is due to magnetization curve, because machine has the same magnetic property. You just changed speed, electromotive force doubled. You doubled the speed, so induced electromotive force will be doubled.